You have around 40 minutes to do your presentation, and then 40 to 45, then plus 15 for discussions. So it's over to you. Thank you.
Of course. Thank you for your introduction, and welcome to this presentation about digital helpers in roller processing, like you already introduced you to. So a bit about myself first. Before I joined Köppern this year, I worked, so I studied mechanical engineering here in Freiberg, at the Freiberg University, at the Institute of Professor Lieberwirth also, and afterwards worked there as a research assistant for 3 years. And now I'm a sales engineer at Köppern here in Freiberg. And for those, I mean, many of you may know Köppern already from their HPGR business, but I would like to introduce you to the company again, in short, for those who don't. So Köppern originally comes from coal briquetting, as we can see here for the for coal briquetting press from the beginning of the 20th century. It was founded in 1898 and is family owned ever since. Oops, it crashed. Nice. I've got to restart PowerPoint.
Yeah, no problem.
Always at the best time. All right. Okay, back again. So it started in coal briquetting, as you can see here with a briquetting press. And the product, roller presses, basically stayed the same since then. The machines only have gotten bigger and much fancier. So also new materials can be processed with these machines, not only coal anymore, of course. And there are over 1,000 roller presses supplied so far or since then. Okay, if we come to Köppern as a company, it's got multiple locations. The headquarters are in Hatting, which is in the Ruhr area of Germany, which is a traditional coal mining as well as a big industrial region of Germany. There we have the main engineering as well as the administration and also the production or slash manufacturing for the machines. But we have also other locations like here in Freiberg, where I currently work. And here in Freiberg, we have the design and sales department for the comminution or HPGR side. And the Freiberg office also very closely works together with our Institute of Mineral Processing Machines of Professor Lieberwirth, both for research and we operate pilot plant together, or our pilot plant is part of the university's bigger pilot plant, where we use the data collected there or data obtained there for our machines for machine sizing, for example, or research and development purposes. Furthermore, there are other offices around the globe, for example, one in Chicago, in Australia, India, or also France. So coming now back to an overview about roller processing in general. So like I said, Köppern comes from briquetting, but since we are at the Global Comminution Collaborative presentation, we are more interested in or many of you are more in the topic of comminution, or the comminution side with HPGRs. But in general, roller presses can be used for two main purposes or two main tasks. Either to the left side for briquetting or compaction, we want to make small stuff big, or we want to make big stuff small with comminution. So at the briquetting side, which is still a current topic, not so much anymore for coal, but for other materials. For example, one really hot topic in a double sense is direct reduced iron, which is briquetted to HPI, so hot briquetted iron. But also at the cold side, cold briquetting side, we have other materials such as metal fines, mill dusts, and more traditional feed material burnt lime or dolomite, which is used for steel making, or the raw materials for fireproof for production of fireproof products. The compaction side, on the other hand, is mainly in the field of fertilizer production, either for single component fertilizers like potash or potassium salts, and also for mixed fertilizers like NPK fertilizers. Yeah, and then finally we have our comminution side with two main directions. First, for ore processing, traditionally in iron ore, either for pre-grinding of the ore or for regrinding of the fine ore as a pellet feed. And of course, many other ores and also industrial minerals can be applied or can be ground with HPGRs, like copper, gold, lithium, or uranium, for example. Traditionally, cement HPGRs come from the cement industry for the comminution of limestone, cement clinker, slag, and so on. But you might already know that. So the roller press used there can have various sizes. Depending on the application, there's a need for different tonnages or throughputs. And it starts with around 1 ton per hour for smallest machine size. And this is for special applications or pilot plant usage, up to the biggest sizes, as can be seen here for one of the largest machines produced, where they can go up to around 5,000 tons. Of course, always depending on the density of the material. So these 5,000 tons are more for higher density ores like iron ore, for example, or others. So design-wise, the main influencing parameters for the throughput are, of course, the roller dimensions. The roller diameter, as it defines the intake behavior, or the roller width as it directly influences the possible throughput. There are power levels up to 5 megawatts possible with machine weights up to 500 tons. So, but irrespective of the process, there are numbers of influencing parameters on roller pressing. Here I've got the two examples of compaction and comminution I want to focus on later on. So these influencing parameters in general on the roller press, or for example, the HPGR or the compacting press, can be described or categorized into 3 different categories, like the machine parameters, the material parameters, as well as the process parameters. So for the machine parameters, we already talked about the machine size, so the geometric dimensions of the rollers. We have the roller surface with a big influence. So for comminution, it's got either stud lining or welded surfaces or hexadual surfaces, which is our own product for the cement industry. Or for the compaction, we have molded patterns, so with small molds or bigger ones for the briquettes, and also the type of feeding system, like a screw conveyor or screw feeder, or normal gravity feeders, like in the cement industry or in the ore industry, have an influence of the machine operation. Then we have the material parameters, which always influence the process. Always important is the particle size distribution of the feed, either for compaction or also for comminution, as well as particle forms, the hardness, the strength, and so on. And finally, we have the process parameters. For example, the material temperature and moisture, or machine settings like the hydraulic pressure in operation, or the roller gap that is built up during operation. And especially the process parameters, which generally change or can be changed while in production, are of interest, as they can be controlled within limits. This makes it possible to use to optimize the roller press operation of the individual process with different kinds of digital helpers. So digital helpers in that case are all kinds of control logics or algorithms that are process or problem specific. And what's a general setup for using such a digital helper, let's say that? In general, we have 2 main ways. We have the more traditional way of directly taking the data stream produced from the machine's sensors and actuators to the PLC. So sensors that are usually on a machine, regardless of the process, are, for example, the gap, the roller gap, the current working roller gap, or the pressure. Also, the material feed temperature is usually measured, or material feed tonnages. And these data streams can then be used for the typical or traditional control purposes, but can also be taken further to the SCADA system and HMI system for further usage. Alternatively, we can also install edge computing, which are basically industrial PCs, where we directly grab the sensor data streams to use for higher or for more detailed automated analysis. Why would you do that? Because usually you don't want to don't use too heavy algorithms on the PLC, as it might be too much for them, and for modeling or live models, you want to use extra hardware that doesn't interfere with the logics and the control system. The output of these edge computing algorithm also can be used further. For example, you can densify the data even further to obtain KPIs, for example, for monitoring the machine. And this is what you always, what you usually think of if you talk about industrial Internet of Things applications, where you have the machine directly talking to your smartphone or tablet, for example. So now I want to come back to the roller press thing, and I want to show 4 different types of digital helpers, starting with compaction, where we start off with a relatively basic but very important digital helper, the screw controller, and then go to comminution, where we have a PMAX control system or control loop, which is based on the PMAX theory of Professor Schönert. The next one would be also staying in the HPGR comminution side, where I want to present you a soft sensor that is used for wear detection or wear measurement online in HPGRs. And finally, I want to come back to a topic I focused on at my work at the Institute, where I mainly did work in the potash compaction granulation part, and that is glazing detection. With this, I want to conclude this presentation later on. What unites these approaches here is, or what unites these digital helpers here is the approach to have a physics-based problem in the roller processing and keep the solution most simple, or as simple as possible, yet as effective as possible. And I first want to go into the screw control digital helper, but before that, I want to first get a look or introduce you to the topic of potash compaction circuits, if you are not too much in that region. So the goal of these circuits is to produce granule of fertilizer, for example, potash, from crystallization or flotation feed material. So this granule usually has the particle size range or granule size range between 2 to 4 millimeters. Why do you want that size range? And this size range is optimal for the application for the farmers, as a fertilizer is spread automatically today. And this size range combines good spreading behavior with good transportation, as well as storage properties, while also maintaining a good solubility in the earth, yeah, for the plants. So the finely dispersed material is first fed to the roller press, or to the screw conveyors on the roller press via chutes, for example. Then the material is compacted to flat agglomerates, these so-called flakes here, in the gap between the 2 rollers. And since the flakes that we obtain are much bigger than the desired product size range, we have to comminute it again. First, it is done via a so-called flake breaker, where we pre-crush the material, and then it gets sent to the first comminution stage, usually a hammer mill, but also impact mills or cage mills more in the American market, and also to roll mills. This comminution stage product will then be screened off at the product or circuit screen, where we get our product material out, our granule, raw granule, and the undersized material will be sent back to the roller press and is compacted again. And the oversized material will be sent to a second comminution stage and will be crushed again or comminuted again there. So this is a typical way of setting up such a circuit. There are also many other combinations possible, but this is more like the traditional way. So in total, a compaction granulation circuit combines the main processes of mineral processing, like agglomeration, comminution, screening, as well as mixing, but also transportation, of course, processes. And if we take a look at this circuit, we see here that the material will have to pass a quite literal bottleneck at some point. And this bottleneck is the active zone of the roller press, which is the smallest area between the rolls. And the roller press itself can be understood as a pump where all the material will have to pass through this smallest area between the rollers. And if we take a look at the throughput of such a roller press, we have a few influencing factors. We have the roller gap first, then we have, of course, the width of the roller. We have the speed of the rollers, and finally we have the flake density or the density in between these rollers. Usually it is assumed to be the flake density, but actually due to the properties, elastic properties of the material, it will be slightly above the flake density. But not only the throughput is limited or influenced by the roller gap, but also the compression itself. If you take a look, for example, at the compression theories of Johannes for compaction, or of Schönert for the particle bed comminution in HPGRs. Here, in both cases, also the compression behavior is somehow influenced by the roller gap, usually in a ratio with the roller diameter, as it influences the speed of the compression, or at least in some relation with it. This leads us to the conclusion that the gap is very important for the machine behavior, both for the throughput as well as for its task, the compression of material. So regarding the throughput, the first logical step would be to increase the gap size as much as possible if you want to achieve the highest possible throughput. But yet it must be noted that this is limited somehow. If you take a look at the product characteristics for potash granules for different compaction settings, so for different specific pressures, which are usually set up in kilonewton per centimeter in the compaction world, and for different gap sizes, operating gap sizes, we see that some of them depend more on the actual pressure applied to the material, and some, like the flake density, depend more on the operating gap size. So the speed of the feed screws will partly define both of it. The feed screws can define a bit of pre-compaction, but also will pull out or will maximize the gap if you spin them faster. Finally, the pre-compaction of material can also increase the gap size. Yet we see that the lower density of the material will lead to a lower class product. So this must be optimized somehow. And on this slide, I want to show you the influence of the different compaction settings on the whole circuit performance. On this slide, you can see two Sankey diagrams for the material streams in such a simple or normal traditional potash circuit, where we have our feed material flow, we have our oversized material product, which is the same amount as the feed, as well as the undersized material. And to the left, we see it for, let's say, worse compaction result, be it through lower temperatures, lower pressure, or bad material properties. These both circuits or Sankey diagrams are normalized to the roller press throughput. So if you take a look here, we can see that when the compression or the compaction is not good enough, the first comminution stage will produce a much higher amount of fines, which will shift the material circuit more to the undersize. And this undersize will then clog up parts of the available machine throughput. So we can feed less material and we will obtain less product as yield. For example, if we have better compaction settings, this shifts way to the oversize side. Usually this is more advantageous and we can obtain a higher product yield for the same throughput of the machine. But remember also this this circuit performance is limited to the upper end. Usually it is the screen area that limits the circuit throughput, as the screen, as all material streams will have to pass the circuit screen at some point. So in general, this means we need the screw control to set up or maintain a preset gap, which needs to be optimized for optimum, is for the maximum highest circuit throughput to obtain the maximum yield while not having too much undersize. If you take a look at another digital helper related to the combination of pressure and gap, you can take a look at the Pmax controller, which is more in the comminution side of roller processing. This applies to roller presses or HPGRs with open circuit hydraulic system, which means where the operating pressure is independent of the gap setting, as well as the compaction circuits with the same open hydraulic systems. In these types of hydraulic system, the pressure is set up via proportional valves and can be directly influenced. So what's the theoretical background for the control logic here for the Pmax control? The base point or base layer for this logic stems from Professor Klaus Schönert, who can be named the inventor of HPGRs back in the 1980s. And he also did a lot of, or where that comes from, he did a lot of fundamental research in the area of particle bed comminution, and later on defined this Pmax theory as a way to calculate the maximum pressure within the roller gap of HPGRs. As you can see here in this sketch, you can see that the Pmax or maximum pressure is applied just above the smallest gap size. And this compression theory can also be used for control purposes. In duration, for example, the Pmax value is mainly dependent on the applied compression force of the hydraulics, as well as the gap size, and of course material parameters, which are described here as the factor CF. To show you the impact of this, we can see two different flake samples that are displayed here for different heights in a piston and die test. And if you think about it as flakes from a HPGR with the rollers here, you can see if you would take a particle size analysis of these samples, you would see that the smaller or thinner flake will have an increase in fines compared to the bigger flake sample taken at the same hydraulic compression, since the gap is bigger in that case. And this effect can be described as a result of these force action lines that which lead the stress towards the edge of the gap and thus reducing the applied stress or pressure to the particles in the middle. So that means that in that area, for the bigger flakes, the grinding effect is limited. In general, the gap formed between the rollers of the HPGR is linked to the applied grinding force, like I said, and the material parameters. And these always fluctuate. They are not constant, and fluctuations can occur. And this means that the applied pressure will change constantly. Consequently, we need a control loop to change the pressure of the hydraulic system in dependence of the roller gap to ensure even energy transfer into the material. Also, there's a sweet spot for the Pmax value. Low values, like we discussed here or earlier, will lead to unsatisfying grinding or comminution results. And high settings or too high settings can increase the wear ratio or may lead to damages on the rollers. So using such a Pmax control loop mitigates these effects, and we can maintain a safe operation of the machine. This control loop can not only be applied to comminution, but also to compaction granulation circuits, which I want to explain here. Of course, this only applies to such systems with open hydraulics. And I earlier stated that the compaction settings will have a drastic influence on the whole circuit behavior. But the opposite is also true. If you take, for example, an increase in hammer speeds of the hammer mills in this case, this would increase the amount of fines which go to the screen and consequently back to the roller press. We learned earlier that this increase of undersize to the roller press will limit our fresh feed. So a way to counteract here would be to increase the gap size or by increasing the screw speed. Yet we know that we have negative effects on the material or on the product properties of a compaction if we only increase the gap size. So we must increase the pressure according to the Pmax value. So we have at least constant Pmax value to obtain a somewhat similar circuit. Of course, it could be technically optimized further if you would increase the pressure much more. You would increase the strength of the flakes. So in one test run or for one test series of potash compaction, we did drop weight tests on the flakes or on the granules. And when you see here the T10 characteristics as well as the obtained A times B values in dependence on the of the Pmax values, you see that with a higher Pmax value, we obtain stronger flakes. And these stronger flakes will then be or produce less fines when comminuted. And this can be a way of counteracting. So the link between the Pmax control and open hydraulics can also be applied to potash granulation to control the circuit in case of changes in the circuit or changes in the material properties, which can be also true for potash plants with different material streams or fresh feed material streams. Now I want to come back to HPGRs and want to present you a digital helper for wear measurement. So in general, wear can occur in different places at HPGRs. For example, we have the wear of the studs themselves and then the wear of the tire or roller core. For the studs, in typical wear pattern, you see a decrease in the length of the studs, but also a change in the shape of the studs as these will be more rounded after a time. If you take a look at the typical wear patterns of on the tire, it's also connected to the studs, you see an uneven wear in axial direction, the so-called bathtub profile, which can be seen here in the picture above. And that bathtub profile is due to the pressure curve in axial direction, where we see a drop off in pressure to the outside of the rollers, which is part of a discussion about flange and no flange rollers and so on. Yet we can also see more types of damage, not normal or catastrophic failures, which could be, for example, such ones where we have washed out material at the roller core or at the tire, which is due to studs breaking off or studs missing, and then the softer material in between will be washed away as there's no material layer in between the studs anymore. So this means the roller wear must be properly measured, and to detect the damages, for example, missing studs or broken studs, early on to prevent serious damages like this. And how to measure wear on a HPGR. So I want to present you a quite common wear measurement method, or the most simple wear measurement method here. And the procedure is basically want to shut down the machine, clean the surface a bit, and then we can measure multiple rows of studs using a caliper as well as a ruler. And with the measurements of the stud lengths and the knowledge of the initial lengths of the studs, we can calculate the remaining lifespan by using linear approximation. What are the advantages here? Of course, low requirements for the measurement. You only need a caliper like this, a ruler, as well as somebody to do the work. Disadvantage here is that it's prone to error, be it human error or due to the dusty environment or dirty environment. Then also we have a low coverage of studs. We only measure a few lines of the thousands of studs on such a machine or roller surface. And the more lines we want to measure, the more time consuming it becomes. So that raises the question if you have any better methods to measure the wear on the rollers. And here I want to present one quite simple solution, which can be found in a soft sensor for wear detection. During operation, the HPGR's roller gap will usually be kept constant by the controls, or by controlling the hydraulics, the roller speed, and the feed system, for example, when using the Pmax control. This means that we cannot see a decrease in stud length by observing or measuring the gap as the distance is measured from the bearing blocks. At the same time, this also points to the measurement of the absolute position of the floating roller, which is movable, and against a fixed point, for example, the press frame or roller frame. And if you take that, for example, and the roller position will change, and we can use edge computing, for example, to calculate the stud length from that, and with the initial stud length again and the geometric data of the roller press, we can expect, or we can estimate the remaining lifespan of the studs. This information can be then forwarded to machine specialists, for example, or we can use it we can create dashboards for the operators to observe the state of the process and machine. The key advantage of this method is that since it's online and the wear rate of studs is usually variable over the lifespan of the studs, this will automatically change depending on the wear rate. Can be thought about like your car's mileage or MPG value that is taken to estimate the remaining range of your fuel tank. Of course, this sensor focuses mainly on the normal wear mechanisms and not the catastrophic failures like stud breakage and the following problems. But there's another system currently in development by a PhD student of Professor Lieberwirth, who is also from Köppern. But I don't want to go into that right now because he will maybe present it in the near future on a conference or another occasion. and I don't want to steal his findings here. So, but now I want to come to my personal topic, which I worked on the last few years, which is glazing detection for compaction granulation. So in some potash plants or granulation plants, we have undesirable effects on the roller surfaces, such as so-called glazing or a material buildup on a roller surface. There, a layer of material starts to cover the surface in one region of the roller. Usually that's in the hottest region just below the screw conveyors or screw feeders, and then starts to cover the whole or most of the roller surface if no action is taken against it beforehand. So because this material layer has a certain strength or thickness, it will have two very negative effects on the plant performance. So first off, it's limiting the actual working gap or the volumetric throughput that is possible. Usually, I saw glazing with glazing layers with a thickness of 3 to 4 millimeters roundabout. And if you think of a typical roller gap in potash compaction, which is in the range of 15 to 16 millimeters, you can say that half of the possible throughput is limited by this or is reduced by this material layer, which we can see here, for example, for the product mass flow of such a plant when glazing occurred. Another problem is we have material that is quite rigid because it is compacted again and again and again with each turn of the machine. And it's also not even. We have some parts or some molds where the roller is still free, and some molds or most molds where the roller is covered with this layer of material. This means that we have changes in the compression behavior of the roller, and this leads to fluctuations, oscillations in the roller gap, in the torque, and so on, which might activate even the vibration sensor and lead to an alarm or emergency shutdown of the machine, which in some plants, like where this photo was taken, can occur up to like 1 time a day. The solution of the plants or of the plant personnel usually was to just let the roller cool down, and then, because the material has some temperature, it will shrink down again and fall out of the molds by itself. But this process takes about 2 hours, and so it will lead to heavy reductions in the plant availability. Another thing could be that if the material layer is thick enough, both rollers could touch and create a torque, create a really high torque that could also trip the machine alarms and shut the plant down. So this is highly undesirable and means we need to counteract somehow. But before we got into a way of counteraction, we need to first find out which parameters influence these glazing occurrence. For this, we conducted a number of different laboratory scale and industrial scale test work to find out which parameters have any influence on the build of material. And this test work was conducted together in cooperation with a German potash mining company. And I could actually do some test runs even on the industry machine with an actual production. So the parameters marked red here are the parameters that were kind of assumed or expected from the beginning, as it was clear from observation that glazing usually occurred in the warm summer times with high ambient and material temperatures, as well as the pressure seemed to have an influence on it. In this test work, I could confirm both influencing parameters, but there are also a number of more interesting influencing factors here. So first, starting off with the time of the material buildup. This does not happen instantly. Usually on the industry roller, it takes about half an hour to an hour to completely cover the roller surface which is the first important information, as it means that we have some time to counteract before the problem is getting really bad. Then we have the particle size distribution, also the material mixture, which influence the glazing behavior. In this specific roller class or plant, we have relatively coarse recycled material, so undersized material that is up to 6 millimeters, which means with a gap of 16, 15 millimeters, we even saw, or we expected, material bridges of these coarse particles to happen. And it's also pre-compacted rigid material. That means that the particles are really pressed into the grooves of the roller surface. Then finally, we have the roller surface condition itself. As newer, shiny, and smooth roller surfaces don't show that or are not prone to glazing as much as used rollers, where we have grooves where the material can directly stick into. So with this in mind, we developed a soft sensor for the detection of the glazing on the roller. As I said earlier, we have a certain thickness, and in the beginning, the material starts to cover only a small part of the roller surface, as can be seen here. And this leads to quite heavy fluctuations in the roller gap, in the torque, as well as in the hydraulic pressure, as the compression changes from time to time. And with these data streams and also other data streams in combination, we can make sure that the readings of these fluctuations can be traced back directly to the glazing on the roller surface reliably. And with this, we now have a method of measuring the glazing or detecting the glazing relatively early on before the whole roller is covered. But now we still need a way of counteracting. And for this, I want to come back to our Pmax control systems I explained earlier on. And as I said earlier, the Pmax value is an indicator of the energy input into the material. And we already know that the pressure or energy input into the potash has a high influence on the glazing problem. So the solution was to install an open loop hydraulic system for a roller press, where the glazing commonly occurred as a way of glazing control. And this was then put into a control loop, or integrated into a simple control loop for glazing conditions, which I want to explain here. So first off, we start with the beginning glazing conditions on the roller surface. For example, due to high ambient temperatures in the summer. We can detect this through our soft sensor, which is installed on an edge computer that was mandated by the client or by our partner, industry partner, as we didn't want to interfere with the control logics. And if glazing is detected, we can first send out our warning to the operators, as well as we can send a signal or Pmax target back to the control system. And these Pmax values are at fixed values, which were agreed on with the industry partner beforehand, as we did some test runs for different Pmax settings to see the influence on the compaction or on the production of the plant. Because we remember that high pressures or high Pmax values are good for the production, and we don't want to lower them too much. So these values are now set up in such a way that it's able to reduce the energy input as much as needed to normalize the surface conditions, but not too much to have a negative effect on the compaction behavior. Please remember at this point that the glazing usually occurs in summer times with high material temperatures, and for potash compaction, high material temperatures are also normally good, but also make the machine more prone to glazing. So this kind of evens out. And when we are back to normal conditions, we can go also back to regular pressure and raise the pressure up again to obtain a similar compression or compaction behavior as before. So this control loop was also patented, and it's in operation at the plant of the industry partner since 2 years now, and they're quite happy with this to conclude. And with this, I also want to conclude the whole presentation, and I hope that I could show you that it's possible to make some impactful improvements to certain processes, here in this case for roller processing, by utilizing sensor data and knowledge that is already equipped on most machines and extracting key information from their measurements. These types of digital helpers can improve machine performance quite significantly, especially if you see the glazing detection and soft sensor algorithm. But there need to be some creative approach to the problem. And finally, IIoT as well as edge computing are key technologies there. As it first, we make it possible that we don't need to influence the control logics, and second, it makes it possible to utilizing the data and building a robust database of sensor observations that allows for benchmarking across different production facilities, for example, to create KPIs. For this, I want to thank you for your attention, and I'm now open to questions. Thank you very much.
Thank you, Johannes, for the very nice presentation. So we have time for some questions. So if you have a question, just raise the hand or open the mic and speak up. I have a question, Johannes, on the, I think it was the case study 3, the wear detection you presented.
Yeah.
You mentioned something about the soft sensor, if I am correct.
Yes.
The use of a soft sensor. My question is, what was the data used as an input to the soft sensor, and what was the level of validation you achieved with the soft sensor? Because it's a very nice information if you can predict online, and it will be available to use as an input to HPGR models to describe its performance. But just to understand a little bit more of this.
So about the data used, it was first used in historic data. Let's say for the first run to set up like the beginning of the and the end of the stud life. Usually we have in our handbook, we have the point where the studs should be exchanged, and that can be used. But what you need to remember there, you need to be wary of changes in, for example, in the zero gap, which can be seen here. Here, the zero gap of the HPGR was changed, and this, of course, changes the calculated stud life. And this is always the same with soft sensors and digital helpers. In that case, you need to be informed about the changes in the actual machine, if you think about that. And afterwards, it was confirmed with the like the data or measurements here was taken over a few years. The measurements were confirmed with the actual measured data of the studs with a traditional method.
Okay, thank you. So, Professor Marcelo has a question.
Yes.
Okay, thanks to you, Johannes. Very nice presentation, and it was nice to see the outcome of your PhD here, even though briefly. But also on this wear measurement, or actually regarding wear and regarding the Copen design, can you mention a little bit of the issue of aspect ratio of the rollers that I see Copen really has typically longer, the experience with longer rollers and not very large diameter, and talking about wear and really developing those bathtubs. Can you talk about the issues around aspect ratios in HPGRs, even though it didn't touch upon, but of course, wear is a big question on that.
Just a little bit. I can go back. Maybe I have somewhere a nice graph, of course. So you may know Felix Heinecke. He did a lot of research into he did some work in the area of the different aspect ratios, and through discussion with him, and also read a paper of him where he talked about the impacts of the different aspect ratios on the on this pressure profile. And generally, the outcome can be said that, or the outcome can be concluded that for a wider machine, the pressure drop or the pressure curve is more even. And if we calculate like the lowest pressure to the highest pressure, like that difference is higher or gets higher, the more or the smaller or less worthwhile the rollers become. And this so with a relatively small or relatively narrow rollers, we can have a much higher Pmax value or maximum pressure in the middle of the roller, which can also increase the pressure, also increase the wear. So the part where we have the edge effect, so that pressure drop off in the middle or at the edges is much higher for smaller or more narrow rollers.
Okay, thank you.
Okay, I'm not sure. Abel also has a question, but
Yes, Müller, thank you so much.
okay. Yeah.
Indeed, it's been such an exciting presentation. A lot of aspects and areas to learn from. I wanted to understand, there was a part where you showed the throughputs for the high pressure grinding rollers, a formula for throughput.
The formula for the throughput of the HPGRs, yes.
Yes.
Yeah, we can go back, yes.
Yeah.
Where do we have it here? So
yes.
that's
yes.
Yeah.
My understanding was that this was only for the high pressure grinding rollers. I wanted to understand whether you could have an idea of what the throughput could be for the cone crushers, because in this one you only talked about the HPGR.
Okay. So about the cone crushers, I can't really go into the formula for the throughput right now because I don't really have it in mind. It's back from the lectures back from Professor Lieberwitz a few years back. But this throughput formula, I mean, this applies to all kinds of roller presses. So either the HPGRs, but also about the compactors as well as briquetting presses. The only thing to consider, or the thing to consider about all types of crushers or machines is that we have to get some volume of material somehow through some gap. It's the same for a jaw crusher, it's the same for a cone crusher, and also for roller presses. And that simply depends always on the geometric values or properties of the specific machines. For example, in this case, it's a simple rectangle. Like we have the gap in this direction, and we have the width of the roller in that direction. And then we have the speed at which the material passes through, which must be calculated differently, of course, for the cone crusher. In the case of an HPGR, it is assumed to be the same as the roller speed directly at the gap, so at the outside of the diameter. And finally, it is important is the density of material within the gap. So for example, if you take a cone crusher, the gap is not completely filled with material. We always have a filling degree of material here. But for the HPGR, for the compactor, as well as briquetting presses, we always assume that the gap is filled completely, which is also not exactly quite true, as we have some drop off at the edges where we have the edge effect.
Okay,
I
thank you so
hope
much.
that somehow solves your question. Yeah.
Yeah, thank you so much. Basically,
Great.
this formula only applies to the HPGR. So thank you so much.
All right.
Okay.
Thank you. So we have another question here from Fana.
Yeah,
Go ahead.
yeah. Hello, Tilio. How are you? Please, in my side, we have the mineral sizer. I would like to know how can we conduct the gap measurement of the mineral sizer, please.
Excuse me. About the sizer.
Yeah,
what
mineral
was the question
sizer.
exactly? Yeah.
Yes, craftsmanship. Yes.
That's a completely different machine than the than compactors or HPGRs, as we have to my understanding, in sizers we always have single particle breakage, and here we have particle bed compression, either breakage or compaction. So parts of the machine behavior are different.
Yeah, that also here it's different. It's totally different with the rollers, but I just would like I want to know that.
Didn't really understand the question, sorry.
How can we conduct the gap measurements of the mineral sizer?
Gap measurement for mineral size. Personally, I would
Exactly.
do the same as we do, for example, the cone crusher. You can, I don't know. For a cone crusher, for example, I would use like a lead pipe, a soft metal pipe where we don't destroy the wear plates or anything. And we can just push it through, and then we can take a measurement of the material inside. But for a sizer, it might be a bit different, as with the tooth of the sizer or the teeth of the sizer, the gap changes, and a metal pipe like this could also tangle up inside.
Do you know with the cone crushers, we can do the lead calibration, and the second one is the secondary crusher. For example, we used to do the lead calibration, and the tertiary one is not the lead calibration. This is the auto calibration. So, but the sizer, the mineral sizer, I'm confused about that. Just so we compensate the gap by adding the metal just to close some But the normal procedure that we like know the normal procedure, how can we take the measurement of the gap?
Yeah, so that would be my idea about the actual gap measurement. But I'm not too much in the topic of sizes, so I don't know of any better methods currently.
Okay. Okay, no problem. Thank you.
Okay, so I think we are running out of time. So I would like to thank you again, Johannes, for the very nice presentation and for the seminar here today. And also thank you all for attending the meeting. So see you by the end of next month, our GCC October seminar. Congratulations, Johannes. Thank you.
Thank you. Bye.
Yeah, thanks for the brilliant presentation. Thanks.
Thank you so much.
Yes, thanks.
Okay, thank you.